For this video, we will be discussing the questions from February March 2023, paper 6.2, which belongs to Probability and Statistics 2. So let's start with question number 1. Okay, we have Anita carry out a survey of 140 randomly selected students at a college. She found that 49 of these students watched a TV program called Bunch. So calculate a 98% confidence interval for the proportion P of students at Anita's college who watch Bunch. Okay, so the keyword here will be the 98% confidence interval for proportion. So we are having two types of confidence interval basically. And then for the confidence interval for proportion, right, the limit should be P. And then upper limit will be plus and lower limit will be minus. Then Z square root BQ over N. So this is the limit, upper and lower limit for the confidence interval for proportion. Okay, so let's find out the calculation now, the value now. Okay, so first of all, we need to have the P lah. So P is a proportion for the students who watch a TV program, right? So P basically should be 49 out of 140. So 49 divided by 140. And I think this is a more simplified form for this fraction. And of course, we need to know what is the Q. Q means 1 minus P lah. So if I take Q minus 1 over P, minus 1, Q equals to 1 minus P, the answer that we get should be 91 over 140. Okay, so now I will want to put it into the 98% confidence interval for proportion. So what is the 98% confidence interval here? So formula should be P, which is 49 over 140, okay, minus the Z. Right, so to get the value for Z, maybe we need to have a look and visualize the idea, right? It is actually from normally distribution, and then 98% means that I'm going to have 0.98 in the center, okay? Right, so to get the value of Z, this is by right the value of Z. Okay, 98% I'm having 0.01 here and also 0.01 here. So that total area under the graph is equals to 1, right? And then after that, if I want to get the value of Z, by right, I should focus on the area below the value of Z, which is 0.99. 0.01 plus 0.98, I get 0.99. To get the value of Z, I will look for 0.99 from the shortcut table at the bottom. So 0.99 area give you the Z, which is 2.326. So when I want to substitute the value of Z in my formula, I'm having 2.326. Okay, then square root BQ over N. Substituting the value for P and Q. Divided by the N. So N is a sample size, right? The number of N is sample size, which is 140. Okay, so this is generally my formula for the lower limit. Then the same thing happens for the upper limit, just that we change it become a positive. So 49 over 140, then plus 2.326 again, then square root. Okay, P is 49 over 140, multiply with 91 over 140, then divided by 140. Okay, so by using calculator to simplify the value, okay, and I will correct it to 3 significant figures. So the answer that we get should be 0.256 and also 0.444. Okay, so this is how we get an answer for 98% confidence interval. Let's proceed to part B. For part B, Carlos says that the confidence interval found in A is not useful because it is too wide. So without calculation, explain briefly how she can use the result of Anita's survey to find a narrower confidence interval for P. So by using the same set of data, right, if you want to get the narrower confidence interval, by right we can change the value of Z. Alright, so to change the value of Z, it is affected by the confidence level. So if you want to have a narrower confidence interval, basically she can change the confidence level to a smaller value. When the confidence level is smaller, it becomes not so wide, right? And therefore, okay, it fulfill what they want, or the Carlos one, she doesn't want the confidence interval to be too wide. So if you change the confidence level, become a smaller value, the value of z will be smaller also. Okay, so you can see the range is become smaller actually. So this is how we answer question number. Okay, question number 2. We are having the number of orders arriving at the shop during the 8-hour working day is modeled by a random variable x with the distribution Poisson. Lambda is 25.2. Okay, so for your information, right, they give us a very clear keyword here, which is Poisson distributed. And then the lambda 25.2 is actually for the 8 hours. So if let's say we are having hours, this is 8, and then our lambda will be 25.2. Okay, they want us to state two assumptions that are required for the Poisson model to be valid in this context. Okay, when we want to have the Poisson model, right, by right, the lambda, so for this case, we are talking about the number of orders. So order arrive must be at a constant rate. Okay, so the orders arrive at a constant mean rate, at a constant mean. Okay, then the second assumption is the orders must arrive at random. Alright, so orders must arrive at random. Okay, then now we proceed to part number B. They want us to find the probability that the number of orders, the number of orders arrive in a randomly chosen 3-hour period is between 3 to 5 inclusive. Okay, then before we can calculate the probability, right, the number of the hour period already changed from 8 hour become 3 hour. Therefore, we have to modify, or we have to get the new lambda first. So we are having 3 hours for our lambda, for our question number B. So I want to know what's the lambda for 3 hours. So to get the lambda for 3 hours, basically what we do is like we take 25.2, multiply the 3 and divide the 8. So I will have multiply 3 divided by 8. So my new lambda for the 3 hours will be 9.45. Okay, so for the 9.45 here, if I want to calculate the probability for number of x is between 3 until 5 inclusive. So you can see that we put an equal sign here. Okay, so to get the probability right, the general formula for Poisson. Okay, so just to recall back very quickly, to get the probability of x equals to r, it should be e negative lambda, and then lambda power r divided by r factorial. This is the general formula for Poisson distribution. So for x equals to 3, I'm having e negative lambda. So x equals to 3 means that lambda power 3 divided by 3 factorial. Then for x equals to 4, I'm having lambda power 4 divided by 4 factorial, and then lambda power 5 divided by 5 factorial. Okay, then when I factorize out all the e power negative 9.45, the lambda will be at outside. So my steps will look something like this. And try to use calculator to help us correct the answer into 3 significant figure, then it should be 0.0866. Okay, so this is how we get the answer for part B1. Then continue further. For part number 2, they want us to find the probability that two randomly chosen 1 hour period. We have two period actually, and each of them is 1 hour. Exactly one order will arrive in one of the 1 hour period, and at least 2 orders will arrive in another 1 hour period. Okay, so now we will focus on the 1 hour period, therefore the lambda will be different again. So now I get the lambda for 1 hour period first. Okay, I'm having 25.2 for 8 hours, so multiply with 1 divided by 8. The lambda for 1 hour will be 3.15. According to the question, we are having one period with x equals to 1, exactly 1, right? Okay, exactly one order will appear or arrive. So x equals to 1. And then for another period, they are having at least 2 orders. So the number of order is greater or equals to 2. At least, so that means include the 2 or more. Right, so this is the result. So maybe this is the first period where x equals to 1. This is the second period where x greater equals to 2. But it can be also the case where our first period is having x greater equals to 2, and then the second period is x equals to 1. But when you have these two cases, right, the calculation for the probability should be the same because they are having, both of them are actually 1 hour period. So to save the time, I will just multiply my answer with 2. That means I'm having two sets of the similar answer, so I multiply with 2. So this is how we set up the question. And now let us start the calculation for the probability. For x equals to 1, you are having e negative lambda power 1 divided by 1 factorial, right? So it is still equals to 1. Okay, so just have this value multiplied with e power negative lambda. After that, for the probability of x greater equals to 2, I cannot find out the Poisson distribution straight away like this, so I have to take 1 minus the probability of x smaller than 2 and then multiply with 2. Okay, then next, I try to combine 3.15 multiplied with 2. So from here, I'm getting 6.3. 6.3 e power negative 3.15. And now I want to put in the formula into the second part here. So x smaller than 2. For x smaller than 2, what we have is e negative lambda. So x smaller than 2 means that I need to include x equals to 0, which is a 1. X equals to 1, where it is always equal to lambda. I don't need to multiply with x equals to 2, right? Because smaller than 2 doesn't include the 2. So I think this is the calculation that I want to include in my solution. Okay, so try to simplify this answer carefully. Alright, by right lah. Okay, by right, you should have this value. I show it into a more detailed way for you to check the answer. So I'm having 0.82216363735. Okay, then simplify all the answer in general. I'm having 0.2219582109, and then I get 0.222 as the final answer, correct to 3 significant figure. Okay, so part C, the shop can only deal with a maximum of 120 orders for any 36 hours of period. Then they want us to use a suitable approximating distribution to find the probability that in the randomly chosen 36-hour period, there will be too many orders for the shop to deal with. Okay, so for our question now, they are going to focus on 36-hour period. So again, originally I'm having 25.2 orders, okay, the lambda for 8 hours. And now we are going to make it into 36-hour period, so I have to change the lambda also, right? Okay, so originally, what is the lambda for 36 hours? So I take 25.2, multiply it with 36, and divide it by 8. Okay, so for the lambda that I get for this question by right, I will get a big number, right? Which is 113.4. And since the lambda is more than 15, therefore I can change it become normal distribution. And for this question also, they actually give us the keyword already lah. So use a approximating distribution to find the probability. Since the lambda is more than 15, which is very large, so I change it become normal distribution. The parameter of normal distribution should be mean and variance, right? So the mean for Poisson is this one, which is 113.4. And the variance for Poisson is the same as the value of mean, which is also 113.4. Alright, so we get the parameter for the normal distribution by putting in the same value for mean and also variance. Because for Poisson, originally the mean and variance value should be the same. Okay, then To calculate the probability, they want us to calculate the probability that there will be too many orders for the shop to deal with. So the number of orders the shop can deal is 120. So too many orders means that X is more than 120. More than that. Okay? So when I'm having the probability of X more than 120, before I calculate the probability, we should know that for Poisson distribution, it is discrete random variable. And then for normal distribution, it will be the continuous random variable. So for discrete random variable, generally we are taking integers for the number of X, right? And then for continuous random variable, we can take any value for the X. Therefore, we need to do some adjustment to change from discrete become continuous. Therefore, we have to apply continuity correction. Okay, so X greater than 120 means that we start from X equals to greater or equals to 121. Therefore, the continuity correction should be 120.5. Okay, so this is a continuity correction. After I change it become the 120.5, I have to standardize it to find out the probability since I already changed it become normal distribution. So for 120.5, I need to standardize it by minus the mean, which is minus 113.4, divided by standard deviation. So divided it by square root of 113.4. Okay, so from here, get the value for Z correct to 3 decimal places, and it should be 0.667. To get the answer for this probability, I have to take 1 minus the area from the normal distribution table. So 0.667, let's have a look for 0.667. Okay, so 0.66 is this one, and then 7 will be 23. We have to add 23 to the last two digits of 7454. Okay, so 7454 plus 23 at the last two digits. By right, we should get 7477. Okay, and after that, I will get 0.2523. And correct to 3 significant figure, it will be 0.252. Right? And this is how we answer question number 2. Question number 3, we are given a diagram and then it is a PDF for a random variable x that takes a value from 0 until 3. The graph is symmetrical at the line x equals to 1.5. When we know that the curve, right, is symmetrical at the line 1 equals to 1.5, basically it also means that the expected value of x is equals to 1.5. So this is the extra details or knowledge that we need to know when we are having the symmetrical probability density function. Okay, it is given that x smaller than 0.6 is A. So if you have a look for the diagram here, this particular area, all right, the value is A. Okay, and then what else did they give us? They also tell us that from the probability from 0.6 until 1.2, it is equals to B, the probability. So the probability also means the area, right? Okay, so for x smaller than 0.6 is A, which is in the red color. And then from 0.6 until 1.2, this particular area I label in light blue. So it means that this area by right, okay, this particular area, the value is B. So from here, if you have a look in details, from this definition, from the information given here, right, if I want to find out the probability that x is smaller than 1.2, it will be equals to A plus B. Okay, so that's information that we can get from what is provided in the question. Alright, so smaller than 1.2 means that you're having the whole area below 1.2, right? So it will be include the red and also the light blue color. So when you want to write out, it should be A plus B here. Okay, so let's come back to the question. For part A, they want us to find the probability that P, the X is between 0.6 until 1.8. Okay, so for the area between 0.6 until 1.8, Again, there are more than one ways that we can solve this question. Okay, there are more than one way that we can solve this question. Okay, if you want, you can try to label out or maybe try to sketch out the area that the question wants us to find. Okay, so 1.8. Okay, 1.8 basically is 0.3 away from 1.5. Okay, so 0.3 and 0.3. So that means 1.8, the value for 1.8 and the value of 1.2 is actually symmetrical on the line also. That means the area smaller than 1.2 will be equals to the area equals to greater than 1.8. Alright, okay, so for in general, the area that they want us to find out is this one, from 1.8 until 0.6. Okay, so this is the area that they want us to find out. Okay, so to find out this area, there are many ways that you can solve it. The first one is to get the yellow color, the highlighted area, right? You can take 1 minus the area below the 0.6, then minus the area greater than 1.8. That's one way. Okay, another way is you can take the area that is smaller than 1.8, that means the whole area, then minus the area that is smaller than 0.6. Okay, so these are the two suggestions that I can give you. If you want to find the area in the highlighted yellow color part, then these are the steps that you can try to consider. Okay, so no matter which method are you using, they will give you the same answer. Right? Okay, so we will start the calculation here. Okay, for the probability of 0.6, x between 0.6 until 1.8 to 1.8. Okay, maybe I can show you both solutions so that you can roughly compare. Okay, let's say I'm using the second method here first. Okay, so for x between 0.6 until 1.8, I can rewrite it become x smaller than 1.8. Okay, then minus the probability of x smaller than 0.6. Alright, okay. For the area, x smaller than 1.8, it is actually equals to 1 minus x greater than 1.8. Okay, then minus x smaller than 0.6 is an A. From the diagram, I can see that it is an A here. Alright, and then what is the area for x greater than 1.8? So like what I mentioned earlier just now, 1.8 and 1.2, right? They are basically refer to the same line, okay, that is symmetry on the graph. So that means if let's say I'm having the area smaller than 1.2, it will be equals to the area greater than 1.8. So I can substitute this one by x smaller than 1.2. X greater than 1.8 equals to x smaller than 1.2. So what's the value for x smaller than 1.2? So I mentioned earlier also in the question, x smaller than 1.2 is a plus b. So it will be minus a plus b, then minus a again. Simplify the answer, I will have 1 minus 2a, then minus b. Okay, so this is the answer that we get by using the first formula here. Then how about if let's say some students they want to consider another method where I'm having this. Okay, so like what I show you here, you can take 1, that means the whole area under the graph, okay, minus x smaller than 0.6, which is the red color, this the white color part here, minus x greater than 1.8, which is this part. Okay, then you can get the yellow highlighted area. So 1 minus x smaller than 0.6 minus x greater than 1.8. Okay, so x smaller than 0.6, basically it is equals to A. It is given in the question just now, right? And then for the area greater than 1.8, you should also know that 1.8 and 1.2 are the symmetrical line on the graph. So greater than 1.8 equals to smaller than 1.2. Okay, so if you try to simplify the answer for smaller than 1.2, right? Just like I told you also, x smaller than 1.2 is A plus B. So substitute into your solution. I'm having 1 minus 2a minus b. Okay, so this is how we get the answer for part A. There are many ways, there are more than one way that we can solve it. Right? So you can just use the diagram to help us, okay, to visualize it clearer and to write out the steps correctly. And this is what we have for question number 3A. Let us continue to 3B. For 3B, they now give us the equation of the probability density function, and this is the probability density function. They want us to show that k is equals to 10 over 81. Okay, to get the value of k, we have to use the property for the probability density function. That means when we try to integrate our function from the lowest limit until the upper limit, okay, for the whole function kx squared, then 3 minus x squared, the answer or the area under the graph should be always equals to 1 because the total probability should be equals to 1 for any probability density function. Okay, so k is a constant, I will just take it out. And then before I integrate it, I will want to expand the function for 3 minus x squared. So I'm having 9 minus 6x plus x squared. Okay, multiply the x squared inside before I can integrate as well. And now I start my integration. I will have 3x squared, 3x cubed for the first term, and then 3 over 2 x power 4 for the second term, then x power 5 over 5 for the third term. And I want to put in the limit for 3 and 0, and it is equals to 1. So from here, if I try to simplify my answer, right, substitute 3 into the x, I'm having 81 minus 343 over 2, 243 over 2, then plus 243 over 5. Then now I want to substitute 0 into the whole equation. I will get a 0 here, and it is equals to 1. So from here, by the use of calculator, by using the calculator, you should get k equals to 81 over 10k equals to 1. And from here, you'll get the value k equals to 10 over 81. Alright, so this is a straightforward question. Just make sure that you don't do any careless mistake for integration. Alright, then next part number 2, they want us to find the variance of x. Okay, so again, same like the discrete random variable. To find out the variance of x, generally the formula will be expected value of x squared minus the value of mean square. Okay, so first of all, I want to find out the expected value for x squared first. Okay, the expected value for x squared, basically it is the integration of x squared multiplied with the function f. If I have x squared multiplied with the function f, right, the x squared originally will become x power 4 because you multiply x squared with x squared. So you have x power 4, and then with 3 minus x squared, I straight away expand it here. Okay, then continue it with the integration. Multiply the x power 4 inside first before you can integrate it. Okay, after the integration, what should you get? Okay, after the integration by right, you should get 9 over 5 x power 5. And then x power 6 for the second term, 1 over 7 x power 7 for the last term here. Substitute in the value for 3 and also 0. Okay, simplify the value. First one, I substitute the 3 into the whole equation here. I will have 2187 over 5. Then minus 729. Then plus 2187 over 7. So this is the value that I substitute 3 into all the terms here. Then now I want to substitute 0 into all the terms here. I will get a 0. Okay, then just simplify the answer. I will get 18 over 7. But this is a value for expected value of x squared. To get the variance, I need this value, 18 over 7, minus the mean square. So the mean square, I already mentioned earlier just now in the diagram, when they are saying that the graph is symmetrical at the line x equals to 1.5, right? So the mean value is actually 1.5 for any symmetrical graph. So I will substitute 1.5 here into my calculation to get the variance. Alright, and if we didn't do any careless mistake, by right we will get 9 over 28, or you can change it become three significant figure answer lah. It should be 0.321, correct, to 3 significant figure. Okay, so this is how we calculate the value for the variance x. So just make sure that we don't do any careless mistake throughout the integration. Question number 4. We have the number of accidents per 3-month period on a certain road has a distribution of Poisson, okay, with the lambda, right? With the parameter lambda, and then in the past value of lambda, it has been 5.7. Follow some changes on the road, the council carries out a hypothesis test to determine whether the value of lambda has decreased. So this is actually the keyword for us to form the alternative hypothesis. If there are fewer than 3 accidents in a randomly chosen 3-month period, then the council will conclude that the value of lambda has decreased. They want us to find the probability of type 1 error in this case. Alright, so before we start calculating the probability of type 1 error, by right we should know how to set up the null and alternative hypothesis first. So they are talking about the lambda. So originally lambda should be around 5.7, and they are going to test whether is it decreased. So that means when the keyword decrease here tell us that the alternative hypothesis will be lambda smaller than 5.7. Okay, and then if you try to look at this particular sentence here, if there are fewer than 3 accidents in a randomly chosen 3-month period, the council will conclude that the value of lambda has decreased. If we conclude that the value of lambda has decreased, it means that we accept the null hypothesis. We accept the alternative hypothesis, right? Because when we conclude that the value of lambda has decreased, that means we have enough evidence to show that this is correct, this is true, and therefore we accept null alternative hypothesis, or we can say it as reject the null hypothesis. Okay, when do we reject the null hypothesis? Again, according to the question, they said if we are having fewer than 3 accidents, then we reject it. We reject the null hypothesis. So fewer than 3 accidents means x smaller than 3. And from here, you actually know that x smaller than 3 will be our rejection region. Because when x smaller than 3, right, we will reject the null hypothesis, or we will make the conclusion that we have enough evidence to accept alternative hypothesis. So this particular value is actually our rejection region. Alright, okay, so from this question, before we can start, first of all, we already know that the rejection region given in the question, where it should be x smaller than 3. Okay, so fewer than, there's no equal sign, therefore it is x smaller than 3, and this is our rejection region. And then to calculate the type 1 error, probability of type 1 error, first of all, we need to know what is the definition for type 1 error. So the definition for type 1 error is actually reject the null hypothesis when the null hypothesis is true. Okay, when will we reject the null hypothesis? We reject it when we are having the test statistic in rejection region, right? So reject null hypothesis means that I will want to put in the rejection region, x smaller than 3, when the lambda is true. The lambda is equals to 5.7, right? Okay, so for this question, the question itself already tells us that we are having x is Poisson distributed, where the lambda is true, and we assume that it is 5.7. To calculate the probability for x smaller than 3, we need to include the probability of x equals to 0, x equals to 1, and also x equals to 2. So according to the formula for Poisson distribution, I'm having e negative lambda. When I'm having x equals to 0, the value is equals to 1 here, multiplied with e negative lambda. When I'm having x equals to 1, then it will be e negative lambda multiplied with lambda. Then when I'm having x equals to 2, then this part it will become 5.7 squared divided by 2 factorial. X equals to 3 will not be included in our calculation here because the sign didn't show the equal sign here, right? It should be smaller than 3, therefore we should calculate the probability up to x equals to 2 only. Okay, so after you write out the steps properly, then you can try to find out the answer from calculator. The long answer should be something like this, and of course we can correct it to 3 significant figure answer, where it should be 0.0768. So this is actually the Taiwan error, the probability of Taiwan error for this particular question. Alright, then we can proceed to part number B. So what they want us to calculate for part number B? So for part B, they want us to find the probability of type 2 error if the mean number of accident for 3-month period is now actually 0.9. Okay, so again, for the type 2 error calculation, we need to write out the definition first. For type 2 error, basically the definition will be we accept the null hypothesis when the null hypothesis is false. Okay, so to calculate the probability for accepting null hypothesis, right, we should include or we should put in the acceptance region. Just now in part A, we already get the rejection region from the question where it is smaller than 3. Acceptance region will be the opposite, okay, of rejection region. So rejection region is smaller than 3, therefore the acceptance region will be x greater equals to 3. And they said null hypothesis is false. Originally, we are having this null hypothesis where lambda equals to 5.7. When they said the null hypothesis is false, that means there are enough evidence to show that the lambda should be smaller than 5.7. So what is the exact value for lambda? If let's say it is smaller than 5.7, so for this question, they basically give us the new value for lambda, which is 0.9. So that means I'm going to use the lambda equals to 0.9 for the calculation in this part. And just to remind ourselves, x is now Poisson distributed with the lambda 0.9. It is not 5.7 anymore. Okay, so to calculate the probability for x greater equals to 3 in Poisson distribution, I have to take 1 minus the probability of x smaller than 3, where it will be includes the step where we take 1 minus the probability of x equals to 0, x equals to 1, and also x equals to 2. So I'm having e negative lambda. When x equals to 1, I'm having the 1 here. Sorry, when x equals to 0, I'm having the 1 here. When x equals to 1, I'm having the lambda, which is 0.9. When x equals to 2, I'm having 0.9 squared divided by 2 factorial. Alright, then again, continue to use calculator and help us to get the answer. Correct the answer into 3 significant figure, it should be 0.0629. Okay, so basically this is how we answer question. Okay, so we are now at question number 5. The mass in gram for large and small packets of max wheat cereal has independent distribution of this one. This is for the large packet and also this is for the small packets. Alright, and then both of them you can see that they are normally distributed. Okay, so to make the calculation easier, right, in my discussion here, I will treat the large packets as L, capital letter L, and then the small packets will be as capital letter S. Right, so for this question, they want us to find the probability that a randomly chosen large packet means that I'm having only one large packet, has a mass that is more than double the mass of randomly chosen small packet. So double the mass of also a one small packet here. For this question, the keyword will be actually double. Okay, so that means I'm going to look for the probability of L greater than 2S. Double means times 2, right? So 2S. Okay, and we cannot calculate the probability when we are having both sides with variable. So I should try to move all the variable to one side where my variable will become L minus 2S greater than 0. Before we calculate the probability, we should try to find out the mean and variance for L minus 2S first. Okay, to L minus 2s, expected value for L minus 2s, it will be the mean for L minus 2s. So mean L minus 2s, basically it is taking the mean of L, which is 410, minus 2 times of mean S, so 206.0. If I try to simplify this value, I will get negative 2. For variance, I'm having L minus 2s also. To calculate the variance for L minus 2s, I will take variance L, which is 3.6 square. For variance, there's no negative, therefore we are always having a plus sign. And then for 2s, variance for 2s, if I want to pull the 2 out from the variance, for this case, I need to square it. So I'm having 2 square with the variance of small packet, which is 3.7 and square. Okay, so there's one part that is worth for us to discuss here. Okay, for the value of variance, right, when you want to take out the constant from variance, basically you have to square the constant where I'm having a 2 square here. So some students might confuse with 2 and also 2 square for the calculation. When do we need to have 2 square? So we need to have 2 square when the calculation is about double, triple, or times, all right, of the original value s. So as an example, the keyword here will be double. Double means 2 times the mass of one randomly chosen small packet. So this one means that we have one packet, one small packet times 2. Therefore, when we want to calculate the variance, it should be having 2 square. But if the question is using this word, when the large packet has a mass that is more than the total of 2 small packets, then for this case, right, if we want to write out the variable, it should be L minus 2s. For example, they will write L minus S1 minus S2. Okay, but if let's say you are writing it, the S1 and S2 by using 2s, right, then for this case, when you want to find out the variance, then the variance will be variance L, okay, plus 2 times of 2 variance x only. It is not 2 squared. So please take note about the difference between the sentence that they are using. So for the original question here, they are saying that we have double the mass of one small packet. So that means you have only one small packet and we times 2 for the small packet. So when you have times 2, something related to times, okay, when we want to calculate the variance, the 2 must be squared. But if let's say they are having 2 small packets, that means you have 2 different packets, they are small packets, and then when you want to calculate the variance, you should add them together, where the 2 shouldn't have any square. Alright, so this is a small details that you should know, especially calculating the question for this kind, for this part. Alright, okay, so let us continue further. Okay, the value of variance should be 67.72 if you didn't get any careless mistake. Alright, then I will rewrite my L minus 2s variable. So my L minus 2s variable will be normally distributed because both are originally normal. So when you're having the linear combination, alright, it is also normally distributed. The mean is negative 2 and the variance is 67.72. Okay, then now we will start to calculate the probability. So according to the question, right, they are saying that one large packet is more than double the mass of one randomly chosen small packet, so 2s, and we are having L minus 2s greater than 0. So just now I already know that L minus 2s is normally distributed, therefore I have to standardize it to calculate the probability. So I want to change it become Z. Value of L minus 2s is 0, then standardize it, I have to minus the mean and divide it by standard deviation. So divide by standard deviation, I'm having square root of 67.72. Okay, then try to get the value for Z correct to 3 decimal places. So I'm having Z greater than 0.243. To get the area for Z greater than 0.243, I have to take 1 minus the value from the table, 0.243. Let's have a look for 0.243. Okay, if I try to enlarge the value, the table here, 0.24. 0.24 will be this one. And then you need to get the 3. So that means you add 12 at the last two digit of 5948. Okay, add 12 at the last two digit. So if I add 12 to the last two digit, then I'm having 0.5960. And then I will get the answer from here, which is 0.404. Okay, so this is how we calculate the answer for L greater than 2s. Okay, now we continue to part B. For part B, the packets are placed in boxes. The boxes are identical in appearance. 60% of the boxes contain exactly 10 randomly chosen large packets, and then 40% of the boxes contain exactly 20 randomly chosen small packets. Okay, so according to the understanding in this question, right, we are having two kind of boxes. One type is they are having 10 large packets. Another type is 20 small packets in the box. They want us to calculate the probability that a randomly chosen box contains the packets with a total mass, highlight the keyword total mass, of more than 4080 grams. Okay, alright, so before we calculate the probability for the boxes, right, for the box, we need to separate out first. So we have two kinds of box. The first one is in the box we are having 10 large packets. So the linear combination for large packet, it is still normally distributed. To get the new mean for 10L, it will be 10 times of the mean. So I take 10 multiply with the mean of L in part A, which is 410, and I get 4100. And then for the variance, right, I will need to take 10 multiply with the variance of the original L, which is 3.6 square, and then I'm having 129.6. Okay, so again, please take note that the 10 here, when I take out the 10 from the variance, right, there's no square for this case because the keyword here is total mass. So total mass, or maybe 10 randomly large packs. Sorry, 10 randomly large packets. So that means I'm having 10 different large packets here. So to calculate the variance, basically we add them together. So when we add them together, it will be just 10 times of the variance B. Okay, and then after that, let's continue. This is the first kind or first type of the box that I have. The second type of box that I have will be 20S, 20 packet of 20 small packets. They are still normally distributed. To get the mean, I'm taking 20 multiply with the mean for the small packet 206, and from there I get 4120. For the variance also the same, because we are having 20, okay, different small packets here. So for the variance, I only take 20 times the variance of S, which is 3.7 squared. There's no square for the 20 as well. Okay, the reason is the same because we are having 20 randomly chosen small packets. Okay, it is not about the time, but they are total. The total for 20 small packets. So the variance also, we just add them together and we have 20 times 3.7 squared. So from this case, we are having the value 273.8. Alright, so for this question, right, they are interested to find out the probability that the box has a total mass more than 4080. So that means I want to calculate the first type of box with 10L and they are having more than 4080 grams. Okay, so again, this is normally distributed question. I have to standardize it become Z. So I will take 4080 minus the mean. So for the mean here, it will be minus 4100 divided by standard deviation. So divide by the square root of 129.6. Okay, so get the value for Z correct to 3 decimal places. We are having negative 1.757. Okay, so if you try to sketch out this area, right, basically it is the same as Z smaller than 1.757. Okay, so let us have a look for the value from the normal distribution table. Where is 1.757? Okay, so maybe we scroll down. 1.757. So what do we have here? 1.75. Oh, I already shown here. 1.7 is this one. 75. This is 1.75, and then 7 will be adding a 6 at the last digit. So 9599 plus 6. When we try to get 9599 plus 6, I will have 0.9605. This is the probability for the box with 10 large brackets, which is more than 4080. Okay, then now we have to continue to calculate the probability that the box with 20 small packets, they are also more than 4080. Again, we have to standardize it, right? Become the exact. So we take 4080. Standardization means minus the mean. The mean for 20 small packets will be 4120 minus the mean, and then divide by standard deviation. So what is the standard deviation that we have here? Square root 273.8. Okay. Find the value of z again, correct to 3 decimal places. I'm having z greater than negative 2.417, which also having the same area as z smaller than 2.417. Okay, then try to find out the value from table. So I think I'll show the result here also. 2.41, which is 9920. 7 will be 1, so you have 9921. Okay, so for this probability, I'm having 0.9921. Alright, and then in the question here, basically we are having 60% of the boxes contain 10L, 40% of the boxes contain 20L, 20 small, 20S. Right, so they are asking for the total mass, the number of box. Find the probability of a randomly chosen box with this mass more than 4080. When you want to choose the box, right, we might get the box with 10L, or we might get the box with 20S. So to calculate the probability for the more than 4080 gram, basically you need to consider the probability that we select 10L and also we select the 20S. So if I get 10L, the probability will be 0.6. And then the probability of 10L more than 4080 will be 0.9605. So this is what we have. Okay, then how about another case is we get the 20S boxes. If you get the 20S boxes, the probability will be 0.4, and the more than 4080 probability will be 0.9921. So we need to consider the percentage of getting the 10L box or 20S box. Alright, so to calculate the probability, we need to consider them and then try to simplify them. The original answer should be 0.97314, and I will correct it to 3 significant figure, and my answer will be 0.973. Okay, so this is how we get the answer for this probability. Right, so this is the last question for this paper, question number 6. Last year, the mean time taken by students at a school to complete a certain test was 25 minutes. And then Akash believed that the mean time taken by this year's student was less than 25 minutes. Okay, so the keyword less than help us to form the alternative hypothesis basically. In order to test this belief, he takes a large random sample of this year's students and he notes the time taken by each student. He carried out a test at 2.5% significance level for the population mean time, mu. Okay, so Akash used the null hypothesis where mu equals to 25. So give a reason why Akash should use a one-tail test. Okay, so from here, right, what is it a one-tail test? So the reason is from this sentence. Akash believed that the mean time taken by this year's students was less than 25 minutes. Okay, so we know that this is a one-tail test because less than tell us that the mu should be less than 25. So how can we explain the answer here? Alright, so you can try to tell them that he actually expects there's a decrease in the mean time, because he expect that the mean time now is less than 25 minutes, right? So he expect there's a decrease in mean time. Therefore, this is a one-tailed test. Right? Okay, so we proceed to part B. Akash finds that the value of the test statistic is z equals to negative 2.02. They want us to explain what conclusion he should draw. Alright, so for this question, we already know that the significance level is 2.5. And then if we try to recall back, our null hypothesis is mean equals to 2.5. And then, mean is equals to 25 minutes. And then the mu is smaller than 25 minutes, right? Because he expects to has a decrease in the mean time. And since we are having the significance level 2.5%, if you try to illustrate it using the diagram, right, our rejection region should be actually on the left hand side because of the smaller sign. Okay, it should be on the left hand side, and this particular area basically is 0.025 lah, which is 2.5%. Okay, I want to know my critical value. Okay, so this is my critical value here. Okay, I try to find the critical value. So let us try to find out first. Critical value is actually this value of z, right? So to get the value of z for this part, okay, you should refer to 0.025, which is the area of the graph. Okay, but too bad in our normal distribution table, they didn't show us the probability 0.025 in the calculation. We have to try to find out the larger value here, which is 0.975. Okay, so if you go to the table, scroll down and look for 0.975. I think there's a shortcut value here, right? Yeah, so for the probability of 0.975, the value of z should be 1.96. If I go back to my question here, that which also means that the critical value here should be 1.96. But because of the z value according to the diagram, right, you can see that it is on the left hand side. Therefore, this value should be negative value, where it becomes negative 1.96. So the critical value will be negative 1.96. Okay, and then if we try to put the test statistic into the diagram, negative 2.02, right? It should be somewhere under the rejection region, because negative 2.02 is smaller than negative 1.96. Okay, so this is the main reason. Okay, we make the conclusion. So since we know that test statistic, which is negative 2.02, is actually smaller than the critical value. Okay, so which is negative 1.96. Okay, therefore the conclusion that we can make is we will reject the null hypothesis. And what's the meaning if we try to reject the null hypothesis? That means that we have enough evidence to show that this is true, right? The alternative hypothesis is true. So you can say that there's enough evidence to show that the mean time is less than 25. Okay, so this is how we make the conclusion according to the critical value that we have and also the test statistic that we have. Then proceed to part number C. In a different one-tail hypothesis test, the z value was found to be 2.14. Okay, So the 2.14 here basically is what? Basically is the Z value. Z value means the critical value, alright? So given that this value will lead to rejection of the null hypothesis at the alpha percent significance level, find the set of possible values of alpha. Oh, sorry, the Z value here by right should be the test statistic. Okay, when I'm having the test statistic 2.14, right, and I try to put it into my test, they are saying that will lead to a rejection of the null hypothesis. Okay, so that means this test statistic falls under the rejection region at the alpha percent significance level. So find the set of possible values of alpha. Right, so again, I will want to draw the diagram to help me again. So, okay, so let's say I'm having my graph like this. Alright, so now they are saying that we are having a different one-tail hypothesis test, one tail also, and then the Z value was found to be 2.14. So you can see that this value are 2.14, right? Basically, it's a positive value. So when you're having the positive value, that means that the one-tail test, by right, it will be focused on the right-hand side. That means I'm having the one-tail test, which is on the right. Okay, then we are having the rejection region, which is actually alpha percent. Okay, and then they are saying that the test statistics, is actually 2.14, and we will find out that this will lead to rejection of the null hypothesis. So that means if let's say the null the 2.14 falls under the rejection region, we will reject the null hypothesis. That means what we can do now is we can assume that the value, okay, the Z value or the critical value, okay, for this rejection region is actually 2.14 or equals to 2.14. Of course the area can be bigger, can be larger, right? Okay, but we assume that it is the borderline, okay, of the rejection and acceptance region. So we can assume that the Z value here is the rejection region, the borderline of rejection region. And by using this 2.14 value, I want to find out the value for alpha. To find the value for alpha, definitely I need to find out this particular region here, right? What is the area for this region? So we are interested to find out the probability of Z greater than 2.14. Okay, so to get the value for Z greater than 2.14, I need to take 1 minus, then find the Z smaller than 2.14 area. Okay, so I'm looking for 2.1 and then 4. You can see that this is the highlighted value, 9838. Okay, so put it into my solution. It will be 1 minus 0.9838. And I actually get 0.0162. So that means the small area here is 0.0162. Okay, and to get the value for alpha, what can we do? Okay, so alpha is actually alpha percent. So that means you have to take the 0.0162 multiplied with 100%. And therefore you get your alpha is equals to 1.62. Okay, but if you try to have a look for this question, right, they're asking for set of possible values for alpha. Okay, and if we have a look for this question again, they are saying that the 2.14 will lead to a rejection region of the null hypothesis. That means 2.14, okay, will give us a result where we reject it. So that means our rejection region can be 2.14, and it will be even better if the rejection region is bigger. Okay, that means the alpha is bigger, then you can see very clearly that 2.14 is fall under the rejection region. So to write out the set of possible value of alpha, we should have alpha greater or equals to 1.62, which means that at 1.62 itself, Okay, when the alpha is equal to 1.62, this area is good enough to represent the rejection region. And I will reject the, and if I have the test statistic 2.14, then I can reject the null hypothesis. But if the area become bigger, right, then very obvious the 2.14 will fall under the rejection region. So it will be good if let's say we are having alpha which is more than or equals to 1.62, so that the result is clear. And the 2.14 actually is the borderline, okay, of the rejection region, the smallest value for the alpha that you can take. Okay. All right. So this is how we get part C. And now let's continue to part number D. Okay, for part D, we have the population mean time taken by students at another school to complete a test last year was m minutes. So this is the population mean time. Sorry carries out a one-tail test again to determine whether the population mean this year is less than m. So again, you highlight the keyword less than m. This is the keyword help us to form the alternative hypothesis. Using a random sample of 100 students, he assumed that the population standard deviation is 3.9 minutes. The sample mean is 24.8 minutes. So this is basically sample mean, which is x bar. And this result just leads to the rejection of the null hypothesis at the 5% significance level. Okay, so they want us to find the value of m. Okay, so how can I find out the value of n? Okay, so generally it's like this. When we want to carry out this test, right, we actually want to know our null hypothesis should be mu equals to m minutes, I think. And then our alternative hypothesis is basically mu smaller than m. Okay, then when we are having the sample mean 24.8, okay, if we try to convert it into the test statistics, the result leads to the rejection of the null hypothesis. That means all this 24.8 falls under the rejection region for 5% significance level. Okay, so it means what? It means that, let's say I'm having this. Again, this is one tail test. So I'm having the rejection region on the left hand side. This value of the area should be 0.05 because of the 5% significance level. And this is my critical value Z. Okay, so for this question, they mentioned that if I use sample mean 24.8 to calculate the test statistics, then the result will lead to reject null hypothesis. That means if I use 24.8 to calculate the test statistics, the value that I get will fall under the rejection region. Okay, so first of all, let's try to find out the critical value first. So to find this critical value, I can't get the critical value from 0.05 area, so I should look for 0.95 area. Okay, so again, go to the normal distribution table. The area for 0.95 is actually this one. Okay, where the Z value should be negative 1.645. How I know that the value should be negative 1.645? How I know it's negative? Because of, according to the diagram, right? Okay, the rejection region is on the left. Okay, so for this Z graph here, the Z diagram here, okay, this critical value should be a negative value, right? Negative 1.645. And what's my test statistic? My test statistic formula, okay, it will be 24.8 minus the mean, which is the m, I don't know, divided by standard deviation, which is 3.9 over square root n, so over square root 100. This is the formula for my test statistics. And this test statistics will lead to rejection of the null hypothesis if it falls under the rejection region. So where it falls under the rejection region, we don't know. Therefore, we assume that it falls on the borderline of the acceptance and rejection region, where this will also lead to rejection of null hypothesis. Okay, That means I am going to let negative 1.645 or the test statistics falls on the critical value. So I'm having 24.8 minus the mean divided by 3.9 over 10. Okay, so try to move all the numbers here and there, right? We can get the value of m here. And if you didn't do any careless mistake, the value of m should be 25.44155, which leads to the 3 significant answer. It will be m equals to 25.4. Alright, so this is basically how we solve this question, number 6. Okay, so this is already the last question for this paper, and thank you very much for watching this video.